Okay, I think it is time to get started again. Should I just take over, Renee? You nod.
Yeah. You just take over and go ahead.
I take that as a yes. Okay. I have the self-confidence just to clear that I should. So there are 3 talks in this session for the next 45 minutes, and then we have time to discuss. I think 2 of these are from Virginia Tech. So Asenath, Kwagalakwe, are you here?
Yeah, I am.
Do you want to try sharing your screen?
Sure.
Because then I would say go right ahead and you have 15 minutes.
All right. Can everyone see my screen?
Yes, we can, and we can hear you too.
All right. So my name is Asenath Kwagalakwe. I am now a 3rd-year PhD student at Virginia Tech in the Department of Geosciences. And today I want to talk to you about what I've been doing on investigating mold generation beneath the northern western branch of the East African Rift using 3D geodynamic modeling with Aspect. So the photo you see is part of the northern western branch taken from Western Uganda. I want to start off by acknowledging my funders, NSF, together with CIG, and all my collaborators listed here from various institutions. So as an overview, I'm going to give a brief introduction of the Northern Western Branch. I'll talk about 3D geodynamic modeling of lithospheric moderated convection and mold generation with Aspect, and then I'll discuss my results and finally conclude. So it's important for us to understand continental rifts because they represent the initial stages of a continental breakup. They could also host precious metals and petroleum reserves. On the other side, they could emit gases like carbon dioxide and methane that could affect climate change. So the major causes of lithospheric stretching are far-field tectonic forces such as slab pull, mantle traction. However, several authors have indicated that these forces are insufficient to overcome the strength of the lithosphere. So what we call here a tectonic force paradox. So there are weakening mechanisms that could facilitate the break of the lithosphere, and one of it is melt. We have pre-existing structures and fluids. Continental rifts can be magma-rich, and this means there is presence of magmatism, but they can also be magma-poor where there is no any evidence of magmatism. The figure you see on the right, it shows the extent of the eastern branch and the western branch of East African Rift, and our study area is indicated here by this box. So zooming into the northern western branch, it consists of 2 segments. It has the magma-poor rift up north here, where there's no any evidence of magmatism, and in the magma-rich rift here, what we also call the Lex George Edward graben, where there's some volcanism taking place here. And the one in the magma-poor, we call it the Albertine Rhino graben. So the volcanoes in the magma-rich area are known as the Tororo Ankole Volcanic Province. The northern western branch is an asymmetric for graben. So on the map here, you see the both lines that you see those are the major faults in the region. And the northern western branch is said to terminate along this shear zone. Around this shear zone here called the Aswa shear zone. The number of earthquakes that have been observed in this region, and they range from magnitude 3 to magnitude 5.9. So our research question is, what is the weakening mechanism allowing the northern western branch to rift? We make 2 hypotheses. The first one is rifting along the magma-rich region, which is the Lex George Edward graben, is due to lithospheric weakening from melt. And then the second hypothesis that we make is melt is generated even in the magma-poor region. However, it doesn't just bleach the surface. So in other words, melt is a weakening mechanism in the northern western branch. So moving on to geodynamic modeling with Aspect. So for us, we use the Aspect code to model lithospheric moderated convection, what we are calling here LMC, and melt generation. So lithospheric moderated convection, this is mantle convection generated from temperature variations caused by the differences in lithospheric thickness. And what this means is when the lithosphere is thin, we expect upwelling. However, when the lithosphere is thick, we expect downwelling, kind of similar to edge-driven convection. We solve 3 major equations: the conservation of mass, Stokes equation, and the energy equation, according to the extended Bose-Nisk approximation, which involves shear heating, adiabatic heating, and we also include latent heat. We use the composite nonlinear rheology, which is a combination of diffusion creep and dislocation creep. And we parameterize melt using the batch melting after cuts in 2003. And this means that melt is formed in a closed system. So melt, there's no melt added to the system, and there's no melt that leaves the system until when the process is done. So we use the Chart geometry where we define 6 sides as minimum and maximum longitude, minimum and maximum latitude, and the inner and outer depth, or also what we call the west, east, south, north, and inner and outer. Our model is time dependent, so we're running for 20 million years, and we set initial boundary conditions of temperature, velocity, depth, density, and viscosity. So as I've mentioned, lithospheric moderated convection is constrained by the thickness of the lithosphere. So we utilize 3 lithospheric thickness models based on seismic observation. So one of it is the Fishwick model. Here it defines, the Fishwick model was updated after 2010. And in our region, it defines the LAB to range from 115 to 143, or 45 kilometers, excuse me. And these values are important to us, as we're going to see in the next slide. So we also use the litho 0.10 after Passianos in Tau 2014, and it defines our region as between 60 and 220 kilometers. And the Alfonso model, which was released last year, it defines our region from 95, the LAB from 95 to 120 kilometers depth. So as you observe, they are all different, and simply because they use different methods to calculate the LAB. But we also presume that the seismic stations that they used to collect data, they were different. So on the map here, the warmer colors, it means the lithosphere is thin, and the cooler colors, it means the lithosphere is thick. So we make we carry out 18 experiments basing on mantle potential temperatures running from 1,643 Kelvin to 1,763 Kelvin based on Rune et al. 2012. However, in his paper, he didn't use the lowest mantle potential temperature here of 1,643 Kelvin and 1,700 and 1,763 Kelvin. So these are n-member cases. They warrant such values low and high according to Rune et al. 2012. So the LAB that we have that I've shown you in the previous slide. So we get that value, we get the minimum LAB, the maximum LAB, and the average, and we extract melt after the model has run. We extract melt at this depth. So this is one of the methods that we have so far used. So the table shows the results where we see melt. So where we see melt, it's a yes, and where there's no melt, it's a no. So as you see up here, it's the magma rich area. We see melt at 65 kilometer depth, and down here with the magma poor on the litho 0.10 model, but down here we don't see any melt according to this formula of extracting melt. So this figure explains just what's in the table. So our study area again. So in the area where we have the magma rich area, we see melt there being generated, but in the magma rich, the magma poor, we don't see any melt being generated there. And these are different models carried out of 1,673 Kelvin, 1,700, and 1,693 Kelvin. So we also go ahead and plot geotherms, and this is one of them for the litho 0.10 model. So we plot, we get a section in the magma rich area and the magma poor rich area, magma poor area. So in the magma rich, we see that there are 3 experiments that cross the solidus. So that means that melt is generated. However, in the magma poor, we don't see any experiment that's crossing the solid, any geotherm that's crossing the solidus. So there's no melt that is being generated. So in summary, our results suggest that sublithospheric melt is not a weakening mechanism facilitating rifting of the entire northern western branch of the East African Rift, specifically the magma poor rift, which is called also the Albertine Rhino Graben. And what's supposed this is the geotherm gradient map plots I've just shown you that we don't see, they don't cross the solidos in the magma pore rift. And another experiment, another supporting point is melt is generated in the magma-rich area, particularly at mantle potential temperature of 1,683 Kelvin, which is a reasonable mantle potential temperature. Thank you so much. I want to apologize that I'll be getting off the call in a few minutes because I want to run to my class, but I welcome questions.
Very nice, thank you. So if you're still around for 5 minutes, we have time for questions. And let me see if I can actually see.
Yes, I see a hand there.
Okay, then go ahead and call on them. I need to figure out how I can see both people. Renee,
That's
you have a question, is that right?
Yeah.
Yeah, that's right.
Go for it.
Hi, Asenath. Thanks for the talk. I really like the results, and I wanted to ask you what you mentioned that the amount of melt depends on the melting model that you use, and that you use an anhydrous melting model at the moment. Have you? Is there any evidence from the melting that is happening in the rift on whether the melts were generated in if there was any presence of fluids at the time when the melts were generated? I don't know the region very well, so I don't know if there is already data.
Yeah, so you mean that in the region where we see melt on the ground, is there any melt generated? Is that a question?
Well, do we know anything about the source rock of that melt? So do we know if maybe the source rock contains some volatiles, which would then mean it would be easier to generate melt at lower temperatures?
Oh, I would answer you in this way. So on ground, yes, when we go to the field, we see the volcanoes there, like we see the volcanic rocks. We have some hotspots there being seen. So yeah, there's evidence that melt is generated there.
Okay, but I was more thinking of like at depth at the location where the melt is originally generated. Are there any petrological observations maybe about the melt? I'm not an expert about this. I couldn't tell you which ones, but
yeah,
I was just wondering, maybe there's information out there somewhere saying if those melts, under which conditions these melts were generated.
Oh yeah, that's something I can look up to see the petrological conditions under which the melt is generated. Yeah.
Okay,
thank you
you
so much for that. Yeah.
Okay, more questions? I'm trying to figure out how I can see a list of all of the people and whether they have questions, but I can't seem to figure it. Oh, here we go. Hi, Jan and Tangchen. Tangchen, you're at Virginia Tech. You can ask her in person if you want to. But Jan, go ahead.
I'm now in Florida. Sorry.
Oh, okay. Well, Jan, go first.
Okay, thank you. Thank you very much.
But keep it quick. We have 2 minutes.
Yeah, I'll ask a very quick one. So, did you set up the potential temperature with the surface adiabatic temperature in the aspect?
I'm sorry, I didn't get what you meant. Could you repeat your question, please?
Yes. So what you show for the mantle potential temperature, is that the same meaning with the surface adiabatic temperature?
So the way I understand the mantle potential temperature is the temperature that would, like if that particular chunk was brought on the surface, that's how the mantle temperature, that's how the temperature of the mantle would be. So are you asking whether they're the same or?
So what kind of model you use in aspect?
So for making the models, I'm using the aspect model, obviously, but the mantle potential temperatures, the way I got the values, I just borrowed them from Rune et al. 2012. So he did some work in the surrounding region, not exactly in our region, but down in the south. So I just borrowed that and then picked and then kind of like added a 10 Celsius addition to see that.
Okay, thank you. Thank you for the clarification.
Yeah, of course.
Okay, Shangxin, do you think you can keep the question to a minute and a half?
Yes, sure. Just
Okay.
Just a very quick one.
Yeah.
Mm-hmm.
Okay. So I have a simple quick question.
Yeah.
Because I think I'm not follow your slides in time when I'm listening to your talk. So my question is that what's the difference of the thermal or buoyancy structure between the magma pool and the magma rich region in your model, or how do you define the magma pool? How do you define the magma pool or magma rich region? By the buoyancy or by other factors?
Basically, we are looking at the physical structures on ground. That's like when you look in the area, we are not seeing any evidence of magmatism. There are no volcanoes.
Okay. Sorry. So I think my question is that what's the difference of the thermal and the buoyancy structure in your numerical model between the magma pool and the magma rich region?
So in the model, we just look at the region. We get the region, how it's like the coordinates. Is it? So we don't put in anything in the code. So we just get the coordinates and like, okay, this region has this kind of coordinates, and that's what we put.
Okay, so
Shangxin, let's keep that for some other time, and let's move on. I'm sorry for cutting you off, but I think we should stay roughly on schedule. Thank you, Asenath.
Yeah, I'm so sorry. Thank you so much. You can reach me on my email, please.
Yeah,
I have to run to class. Yeah.
Okay, so the next talk is by Alireza Bahadori from Lamont Doherty, and please go ahead.
Thank you. All right, I'm switching to the full screen mode right now.
Yeah, looks great.
So I assume that everybody is able to see the first slide in the full screen mode.
Yep.
Thank you. So the title of my today's presentation is how do deep forces from inside the Earth combine with climate and surface processes to shape the landscape? During my work with my PhD advisor, Bill Holt at Stony Brook University, and also my work with my current postdoc mentor, Jackie Osterman at Columbia University, I have been investigating the paleogeodynamic evolution of the southwestern North America and also the East African Rift System in terms of three principal driving forces for the formation of the continental lithosphere. And then those driving forces include the buoyancy forces, the plate boundary forces, and also the basal tractions, which are associated with coupling between mantle flow and also lithosphere. Today, I will first talk about our numerical modeling work for the southwestern North America first, and then I will talk about the numerical modeling that we are doing right now for the East African Rift System with aspect code. One important thing about the plate tectonic history of the southwestern North America is that there is evidence of a flat subduction of the Farallon slab underneath the North American plate, and this has been obviously recognized based on the migration of volcanic arcs from west to east when the slab was flattening. And then following this flat subduction, we had the lithosphere foundering and a slab rollback of the laterite flat subduction during 45 to 30 MA that resulted in crustal extension, formation of the basin and range province, together with the development of metamorphic core complexes there, which are shown here with blue spot. So metamorphic core complexes are usually found in areas where the ductile middle and lower crust is exhumed at the surface through a low-angle detachment surface. To explain the mechanism responsible for landscape evolution in southwestern North America, we develop numerical models that take into account all of the important key elements and driving factors that were responsible for landscape evolution and also metamorphic core complex formation. And the models that we have developed take into account the coupling between mantle convection, lithosphere thermomechanical evolution, and also the surface processes. All right. The first driving factor for landscape evolution that we investigate is the effects of traction field and temperature evolution associated with mantle convection following a slab rollback below the North American lithosphere. And we investigate this effect through one-way coupling of the mantle flow with lithosphere. And to do that, we first produce time-dependent tomography-based mantle flow models. And this will result in a 4D mantle convection simulation and also the associated sublithosphere traction field. So we use the finite element software aspect to simulate the temporal evolution of global mantle flow from backward mantle convection to the late Eocene, and to perform the simulations for the southwestern North America, we use the global density distribution model TX 2008. Here we see the radial cross sections of the reconstructed mantle temperature variation from the surface to core mantle boundary at latitude 38 degrees north, and then superimposed on these cross sections are the corresponding mantle flow velocity vectors. So the main point, or maybe the useful outputs of this mantle convection model are the spatial and temporal variations in the 3D stress tensors and the associated traction fields at different depths. So these panels that you see here in this slide, these panels show the evolution of the traction field associated with mantle convection at 200 kilometer depths. And the vectors here represent the horizontal component of the traction field, and the contour lines represent the radial component. So the point here is that by using these traction fields as the boundary condition at the base of the lithosphere, we perform the one-way coupling between mantle flow and lithosphere deformation. The other driving factor for landscape evolution of this area that we investigate is the effects of gravitational body forces caused by gravity acting on the 3D lithosphere structure. So the need here is a reconstructed crustal structure before the onset of extension and topographic collapse. And also, obviously, the advantage of having a reconstructed crustal structure is that we can use it in a forward modeling simulation to investigate the depth-dependent body force effects with a viscoplastic rheology for cross and also upper mantle. So now here you see the final integrated crustal thickness model that we have produced at the late Eocene based on backward integration of the strain rate history through time. And the reconstruction shows a 60-kilometer thick cross at the late Eocene, which we interpret this to be associated with the severe and laramide orogenies that happen in this area. And also our final integrated paleo elevation model based on backward integration of a strain rate through time generates highlands in southwestern North America. So one important thing here is that the reconstructed location of present-day core complexes lie within zones or belts where the crust was thickened prior to extension. And we think that this is an important result suggesting that there is perhaps a causal link between high topography, crustal root, and core complex formation. All right, so now that we have a reconstructed crustal structure and surface elevation, we can go ahead and do the setup for our 4D forward thermomechanical simulation. And here is just a representation of our lithosphere model geometry, temperature, boundary condition, and also a strength profile as a function of depth. So you can see that we use a creme brulee model for the basin and range area. We use a jelly sandwich model for the cratonic part. We use free slip boundary on the sides. And also we use traction fields that are associated with mantle convection at the base of the lithosphere one. But there is still one more thing here. We have the third driving factor for landscape evolution in southwestern North America, and that is the effects of surface erosion and mass redistribution. And we investigate this effect through the coupling of lithosphere tectonics with surface processes. So here is what we get after we do the 4D forward model simulation. So you can see that the model predicts that the collapse of the highlands in southwestern North America is associated with high gravitational body forces that are initially available. And then you can see that the magnitude of velocity is bigger in areas with high elevation and thick crust. So this forward model run suggests that high GP of a mountain chain could have generated deviatoric tensional stresses that were a fundamental driving mechanism for extensional collapse in southwestern North America. So now, because the 4D model that we had developed did not have a high resolution to capture all details for a structural evolution of the crust, then in a follow-up work, we decided to run high resolution 4.5D simulations to better investigate the main factors controlling the metamorphic core complex formations. And then in terms of the model setup, we have run 6 models with varying crustal structures. And for the first 3 models, we use a traction field at the base, which is associated with mantle convection simulation, and we apply free slip boundary conditions to the side. And then for the second 3 simulations, we apply a pressure equilibrium boundary condition at the base, and we apply a constant velocity boundary condition on the left. So as you see in this animation, model 1 with a crustal root and non-uniform distribution of GPE together with a traction boundary condition at the base shows the formation of a metamorphic core complex. And this model that does not include any predefined extensional boundary condition can explain the formation of core complexes in the northern cordillera of North America during the subduction of the Fallon slab underneath the North American plate. So in this simulation, as you can see that as the moho rebounds, the upward motion of the lower crust and upper mantle localizes a strain in the upper crust below the highlands along a conjugate shear zone first, and then later on, the strain localization happens along a main detachment. And then our model shows that the final stages of core complex geometry involve a low-angle detachment surface that exposes the brittle ductile transition at the surface. And then finally, we end up with formation of basins and ranges at the end of the simulation. So now, model 4 with a crustal root, equal pressure at the base, and a far-field extensional boundary condition also predicts the formation of a metamorphic core complex through time. So this model with a predefined extensional boundary condition on the left can explain the formation of metamorphic core complexes in the central and southern cordillera of North America when we had transtensional stresses there after the East Pacific rise subducted beneath the North American plate. All right, so now I want to switch to the East Africa and talk a little bit about the numerical modeling that we are doing for the East African reef system. So obviously, I assume that all of you know that the East African reef system started forming roughly at about 22 to 25 million years ago. And because of that, the African plate is in the process of splitting into 2 tectonic plates, the Somalian plate and also the Nubian plate. And then we know from the seismic data that right below the reef, the rise of a large mantle plume is doming the lithosphere upward and causing it to break as a result of the increase in temperature, which is followed by a stretching and also breaking by faulting. So for the East African Reef System, we again start by running and reconstructing the mantle convection back to 30 million years ago. And we then create a reconstructed crustal structure and surface elevation. And then after that, we start the forward modeling with aspect. So here the panel on the left shows the radial cross sections of the reconstructed mantle temperature variation. This is at latitude 4 degrees north. And then the panel on the right shows the magnitude of the dynamic uplift and also the elevation changes associated with the mantle convection model. So as I just mentioned, after running the mantle convection simulation back to 30 MA, we do a reconstruction modeling for crustal thickness back to 30 MA as well. And this reconstruction is done based on considering the plate motion history through time. So now here on the right, you see the reconstructed crustal thickness structure for the East African Reef System that we have produced. This is for the Oligocene time. And so here we see that the cross has been thicker before the onset of extension. So the panel in the middle here shows the reconstructed surface elevation based on isostatic compensation of our reconstructed crustal structure, together with elevation changes associated with our mantle flow model. So we do the isostatic compensation for the crust first to determine surface elevation, and then we subtract out the total dynamic uplift from the surface elevation model that we have already produced. All right, so now that we have a reconstructed crustal structure and surface elevation together with the reconstructed temperature field at 30 MA based on backward mantle convection model, we can go ahead and do the setup for a forward thermomechanical simulation with aspect. So as you see here—
1 minute.
All right, as you see here, we create or reconstructed 3D crustal structure at 30 MA with aspect, and then we differentiate that reconstructed crustal structure. But our goal is to develop fully or two-way coupling of asthenosphere and lithosphere for the East African Reef System through time. So here in this case, instead of running a mantle convection model separately and extracting the traction field and then putting it into a separate model for a lithosphere model, kind of like what we did for Southwestern North America. So now we are working on models that have the full coupling between lithosphere and also the asthenosphere. And obviously, we are taking advantage of the adaptive mesh refinement that is available in ASPECO. The other thing is that the temperature field for the lithosphere at 30 MA in our forward model simulation is defined based on a linear geotherm with a thermal boundary condition at the surface, which is 273 degree Kelvin. And then we also have a laterally varying temperature field at the base of the lithosphere at 200 kilometer depth, which is determined based on backward reconstruction of the mantle convection. So we need to create that temperature field in 3D for the lithosphere because we want to use that temperature field to create a strength profile for the lithosphere. And then we are also using a linear or Newtonian viscosities for the asthenosphere all the way from the area below the lithosphere to the core mantle boundary. And then for the lithosphere part, we are using nonlinear flow laws, and then we run both nonlinear and linear flows simultaneously. So now I just want to— Can
you show us the result slide maybe? And
yeah, I just want to—
I just want to make sure that we stay on time.
I just want to spend maybe a minute and a half to quickly show you the result at 4 degree north for one fully coupled simulation that we have run for especially for the Turkana depression area. So now here is actually what we get after we run the model for 30 million years, starting from the Oligocene time. We have the lithosphere, the 3D structure of the crust, and then we also have the absolute values of the temperature. So the main point here is that in our simulation, the conductive heating weakens the lithosphere, and then the thermal erosion and basal shearing of the mantle lithosphere below the rift system progress within areas with high magnitudes of the starting gravitational body forces. And I think I can end here, maybe after we are done with this movie. So here I zoom in to this part of the lithosphere below the Turkana Depression to look at what is really happening to the starting crustal structure. And you can see that the thermal erosion of the mantle lithosphere and overlying crustal extension results in the thinning of the 50 to 55 kilometer crust that we have initially, and then we end up with a 25 to 30 kilometer crustal thickness, which is close to what we see from the crust 1.0 data set. And then the final thing is that to constrain the model more, we are using thermochronology data. We are taking advantage of the tracers that we can put into aspect to extract the pressure, temperature data set to figure out if the cooling rate that we are getting from our thermomechanical model is close to what has been already observed based on the actual measurement using the techniques for low temperature thermochronology. So thank you for listening.
All right.
I can stop
well,
here.
Thanks very much. So let's postpone all of the questions to after the last talk, when we have 45 minutes for discussion. And let's move on to the next talk. Grant, are you there? Yes,
I am here.
You are. Then go right about it.
I will do just that. If everybody can see and hear me.
Yes,
then...
we can both.
Great. I will jump right in. So thanks so much, everybody, for sticking around to the final session of presentations. I just was in a similar situation in AGU where I had a very late presentation. It's always good to know you still have some audience in the last one. So the talk I'm going to give for a couple minutes today is going to be slightly different than a number of the talks we've heard over the past 2 days, in that I'm going to focus in on models that were run for benchmarking purposes. So this is a paper that is currently in review. Most of my co-authors are here at this meeting with me. This is work that's being done to really test some simple and known cases that have been published in using separate codes before, see how aspect compares to those other results, see how they're similar, how they're different, and I'll walk through what we've been doing. So I kind of just want to start with why do this at all? This is benchmarking is something that we all know. Obviously, this is a crowd I don't have to give a long explanation for this, but ultimately, I just want to point out that over the past several decades, computing has really evolved quite a lot, pretty rapid change, and it is always important to go back and ensure that what you are calculating is ultimately in agreement with things that have been done before, or if it's different, why is it different? So I'm going to look at some cases and talk about how they compare and contrast with how they were run with a previous code. So the cases that I'm going to talk about come from a benchmark paper, Zhang et al. 2008. This paper did some 3D spherical shell testing, both thermal and thermochemical in compressible models. They ran these using CitcomS, which is another geodynamics code that's existed for a number of decades. Several of the cases that they presented on, they also had some results from other codes, other publications that they pulled in to compare, but many of the tests were just run for that paper. So for this work, we picked a selection of those tests and ran them using both Aspect and CitcomS. My advisor, Scott King, reran a number of tests using CitcomS to do a direct comparison. And then myself and Shanshin Liu did some running of the Aspect models to see how they compared. The authors of the Zhang et al. Benchmark specifically analyzed a couple of parameters and presented them for each test, namely the root mean square velocity, the average temperature, and then Nusselt number at the top and bottom of the spherical shell. So for all of our tests, we analyze these same properties and list them as well. As you may have seen from the title, or if it slipped by too quickly, because the title is very sort of verbose, this is for Rayleigh numbers that are sort of low to moderate on the order of 1,000 to about 100,000. So this is a little bit lower than you would expect for, say, the Earth's mantle, but makes good testing ground for simulations just to see how a code is performing. The major difference between any of these individual models is how the viscosity varies from the top to the bottom of the model. Some of them are constant. There is no change of viscosity at all. It's held constant throughout. Some of them have very large changes from the top to the bottom. And the other major thing that I will show you in just a moment is the actual plan form. Most of these, they have a starting initial perturbation, and several of the models hold this shape throughout the run. Some of them change if they have particularly vigorous convection. These models are all, they use non-dimensional inputs, so all of the values are switched to non-dimensional, either 0, 1, or somewhere in between 0 and 1, which means the Rayleigh number is controlled by the gravity value alone. If I want a Rayleigh value of, say, 7,000, in some of the cases I'm about to show you, that's what it is. I would set the gravity to 7,000, everything else is 1s or 0s. It is important to note that in a number of these cases, there are actually two different solvers for aspect that are being tested. This is done because in initial tests several years back, it was noted that there was good agreement for a few of the parameters, but the Nusselt numbers for some of the aspect tests were slightly further off than were expected. So I actually helped design a benchmark in a hackathon a couple of years back that could test very simple prescribed flow, see where heat was going. At the same time, SUPG was being implemented into Aspect's default energy solver is the entropy viscosity solver, and so SUPG was implemented at a similar time. And so looking at the two, this is taken from a figure that is part of the paper that's in review. The top two cases are using entropy viscosity, and the bottom two cases use SUPG. The left have pretty coarse refinement. The right have a more refined grids. So what you can see is that if you have grids of a certain refinement level, the solver scheme that you use really doesn't matter. The solutions are pretty indistinguishable from each other. But as you coarsen out, you'll start to see a little bit of difference. EV occasionally shows that it does not hold on to heat quite as well as SUPG can. I'll show you some of the results showing that there is a difference between the two, though they do converge pretty quickly. So for most of these tests as they were run, SUPG was used as the solver scheme in Aspect. This also keeps it in line with CitcomS, which uses SUPG for its solving as well. But more recently, several of the models were run again using EV because a lot of work has been done through time on that. And so those results are presented here as well. So unless I say otherwise, the Aspect results are calculated using SUPG, but you'll see some cases with EV results as well. So this is a quick look at a visualization of the models that were picked from the Zong et al. Benchmark paper. The top three are what we call they're from the A cases in the paper. There are a number of cases listed simply as A1, A2, A3, and so on. These are tetragonal in shape. You can see that in the first two. They have an initial spherical harmonic perturbation that gives them this 4-plume structure, and it remains throughout for a number of the models. Some of them just keep this shape all the way throughout. It's easy to see. The one on the end, A7, is one of the more complicated runs from the paper. You can see that there's a large viscosity contrast for that one, which causes much more complex convection to take place. So it's a bit more of an interesting shape going on. The bottom three models are from the C cases. These ones are called cubic. They have 6 plumes instead of 4, so you can envision them as sort of touching the centers of the 6 sides of a cube, so they are cubic. This is achieved by doing 2 spherical harmonic perturbations at the beginning of the run, so that actually is a modification that's been made in plugin form to be able to do 2 spherical harmonic perturbations simultaneously to make these shapes appear. So I am going to go through and show you some of the results from the paper, how they merged together. This is an example. I have those same parameters I listed at the beginning, the root mean square velocity, temperature, and Nusselt numbers all plotted out next to each other. They're going to look something like this. Your various symbols you have on here, the black diamond on there, are what is the value that was reported in the Zhang et al. Benchmark. All the red triangles and red lines are CitcomS results that were run for this paper. And then blues are aspect results, as are yellow. If you see both blue and yellow, then blue represents SUPG results and yellow represents entropy viscosity results. And dashed lines, if you take all of those data points, we took them and we ran a Richardson extrapolation once we had all of these values to get a sense of what the overall trend of these data points seems to be. We use that as a sort of approximation for an theoretically infinitely refined grid. So you can see where all the points are trending. You can see how the codes are trending for these various values right next to each other. So let me run through one or two of these cases with a couple of minutes I have left. So A1 is the sort of starting case here. It has a constant viscosity throughout, a delta eta of 1. The Rayleigh number is 7,000, so we're on the low end of the spectrum. It is one of the tetragonal cases. And on the left, you can see our various results comparing aspect and CitcomS. It should be pretty quick to see that for temperature and the two Nusselt numbers, all three of the results, the two codes converge really, really well. They all come together extrapolated to about the same place, even if the paths they take are slightly different. CitcomS in particular for the temperature takes a bit of a tight or a higher swooping path down to get where it needs to be. You can see that aspect at coarser grids is able to much more quickly find where the ultimate extrapolation goes with higher and higher grids. There's slightly more difference in the root mean square velocity between the two codes, but if you look at the y-axis, you can see that it is not an extreme amount of difference. It's actually still a very small amount of difference. You can see that for this case, which is a good starter case and a fairly simple one, things are all in line, things match very well. Case A7 is one of the more complicated cases. You can see that for root mean square velocity, aspect and CitcomS actually take slightly different solution paths, but ultimately they end up at very similar values. The remainder of the values are not quite as varied as that one. The solution paths are fairly similar. You can see some slight difference between the two codes a little bit more easily here. I will also note that my Nusselt number plots on the bottom, those occasionally will have more white space than you might expect for certain plots. I hold the y-axis minimum and maximum values constant between the two Nusselt number charts that you can really see the difference in how those two are changing. They should, in a perfect world, they should really stay as really, really similar values. So in order to really show that, I hold those constant. I'll also show one cubic case here. This is C1. This has a constant viscosity throughout, just like A1 did, but the Rayleigh number is higher. These are the more moderate cases at 10 to the 5th instead of 7,000. And it, of course, is the cubic 6 plume case. Once again, you can take a look and see temperature and the Nusselt numbers for the two codes really are very much in sync. You can actually see that entropy viscosity really hones in on those heat values more quickly than SUPG does. And once again, VRMS shows a little bit of difference between the two codes, but nothing extreme. They are still very, very much in agreement for all the cases that were tested. So kind of quick conclusions to this whole thing. There are more cases in the paper that I didn't go over here, but just the general conclusions are the two codes are in excellent agreement for all of these parameters. A value that is used for each test that we use to test further how accurate these tests seem to be is taking a look at the difference between the top and bottom Nusselt numbers. In a perfect system, the heat flow in should perfectly match the heat flow out. So taking a difference of those gets for all cases tested, aspect can achieve within a 1% difference of those two values for all the A cases, and it needs a 16 radial cell mesh to do that. The C cases, it needs slightly higher, 32 radial cells, but all of these results are achievable with coarser grids than CitcomS requires in order to get similar results. So I believe that's really all I have for you. Thank you so much for your attention.